Hello, this is Jonathan Gardner, and as part of my Theory of Python series, I wanted to go over Unicode, ASCII, UTF8, encoding, decoding, codecs, all that kind of stuff, what that means, and what you need to know. So I'm going to try to dive into some of the details of Unicode. I obviously can't do justice to it. It's 1,000 pages that you need to read if you really want to understand what it's all about. But I am going to help you understand what you need to know in order to handle this. And before I begin, I just wanted to tell you that if you're not too interested in the details of what's going on, all you really need to know is that you take a string, I'll just put S, and you're going to say encode. And then when you get bytes or input from a user or you're reading from a file on the disk, you're going to do b.decode. And by default, Python is going to use the UTF8 encoding, which 99.9% of the time nowadays is the right option. It's generally what you want to use. If you know you need to use a different encoding, then you can put the name of the encoding in the string of encoded decode. But if you're doing that, then somebody's going to tell you, or you're going to realize that you need a different encoding. So that's basically all you need to know. Okay. So moving on, let's talk about what Unicode is. So Unicode is a standard that started back in the late 80s. I think it was Xerox and Apple that had some people get together and said that they needed to solve this problem of encoding. And by that time, they realized it's going to be a big issue, and they wanted to have a universal solution for everything. So what's a standard? Well, in computer programming and computer science, and pretty much in any industry, standards are things that we all agree to use so that we can interoperate together. So in the terms of programming, Unicode is the standard we use to deal with text, right? So it tells us how we represent text, how we can read and write text, things like that. The Unicode standard is a document. It's maintained by the Unicode Consortium, which is a partnership of multiple large corporations that you've heard of. Some countries are in there as well, representing their languages. And it's a very big deal, okay? And there's lots of these little, I wouldn't say little, but there's lots of these groups and organizations throughout any industry, really. And they get together and they decide these standards by coming to agreement or consensus or somehow driving, a solution that everybody can agree to is the right solution. So Unicode is that solution that people are driving to. Now, Unicode isn't perfect. There's a lot of people that have complaints with it. There are some things that probably need to be fixed eventually, but it's a great solution for the current state of the way things are. And it's really been adopted very heavily throughout the industry. So we don't see a lot of competing standards out there for Unicode or things like it. And Unicode does have a goal of eventually encoding everything. Like everything that can be encoded will be encoded using Unicode, which I think it's a goal. I think it's achievable. I think it actually is possible. Okay. So let's talk about what encoding is. When we talk about encoding and decoding and the word codec. Okay. So these three words are related. So encoding is when you take some idea and you turn that into a sequence of bytes, okay? And decoding is the reverse, when you take those bytes and you convert them back to the ideas. I guess there's ideas plural there. So this is called encoding, and this is called decoding. And the codec describes how the encoding and decoding works, okay? So for instance, UTF8 is a codec, okay? It describes how you encode Unicode to a sequence of bytes and how you decode a sequence of bytes into Unicode. Okay, this is a pretty generic concept throughout computing. It's something that you're going to see over and over again. So get used to these words. This is how they're used. Okay, ideally, a codec should allow the ideas when they're encoded and decoded to be restored 100%. Right, so there should be a 100% mapping from things over here to things over there. So let's talk about language and encoding language and all that kind of stuff. So a bit of a history lesson. So how do humans communicate thoughts? Right, so we have person A over here, and he wants to communicate ideas to person B over here, right? And vice versa. So how do we communicate those thoughts? And since we don't have telepathy yet, traditionally you're going to find that they use speech. Nobody knows when humans started speaking, right? It's probably something that happened very early. It may be even the thing that shaped humanity into what it is today, right? We do know, however, that the earliest instances of recorded writing comes about 3400 BC. So we have artifacts of people writing and communicating with each other through written language in 3400 BC. Now, writing is pretty awesome because once you write it down, it's preserved in time. Okay, it doesn't change over time. Like your writing doesn't magically change. Like if I took this piece of paper and stored it in a cabinet somewhere and pulled it out 10 years from now, it would be the exact same. Okay. Obviously, some things decay and stuff like that. However, speech, it seems every generation wants to add their own little flavor of pronunciation or their new words or whatever. And so speech is constantly changing. And there was a really interesting video somebody did that was about how you can travel. Like if you were to travel back in time, would you be able to communicate with your ancestors? The answer is no, you probably wouldn't be able to. Now in writing, there's basically two writing systems that started. Well, there's one that started. You basically have ideographs. You have little pictures that represent ideas. And then over time, what developed was a system of letters where you had little simple ideographs that represent sounds. This is like the Latin alphabet and the Greek alphabet that we have today. Okay. Morse code is when we started wanting to communicate over electric wires and radio signals. And this started in 1837. It was developed by Morse and others who were building the first telegraph machines. And they used a systems of dots and dashes to represent communication. So this would be dot, 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 dash, 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 dot, dot, dot. And if you're doing Morse code, you don't say dot and dash. You say dit and da, right? So dit, 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 da, 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 dit, 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 right? Also in Morse code, something that's kind of ignored is the spacing between these groups of dits and das was important. Longer spaces would represent a separation between words, and shorter spaces just between letters. Okay, so you can use this to send text over telecommunication wires, radio frequencies. Anything that has a binary state on and off. You can use lights. I think lights. During ships would use lights during a storm to communicate. All these kind of things that were used, and this was an international standard. I believe that it's no longer a maritime standard, meaning that if you're running a ship in the ocean, you don't need to be able to communicate Morse code. And it gave us 26 letters and 10 digits and some other things. So basically everything we needed if we were speaking English or using the Latin alphabet. Okay. About 1960, people were working on teletype machines, and so they wanted to communicate electronically. Morse code was great, but it was very difficult to encode into the electronics itself. So they wanted a system that had, a consistent spacing for each letter. Okay, and so ASCII was introduced in 1960. It was developed by the ASCII organization, which later became the ANSI organization. This is the American National Standards and Institute, I think it's what it's called. And latest version was updated in 1986. Okay, ASCII is used extensively on the internet. And ASCII is actually, Unicode recognizes ASCII as fundamental. It's been shared by many, many languages. And so what ASCII does is it takes the numbers between 0 and 127 and assigns to them 95 printable characters and 33 control codes. Okay. Many of the control codes nowadays are obsolete. They don't mean anything. Now, one of the problems with ASCII is it does a great job for the basic Latin alphabet, which English uses. It doesn't do a great job at all for, French or German or Spanish or any of those other languages. And so people got the idea of using the numbers 128 through 255 for their extended character set. And so we get things like ISO 88591 and ISO 8859115. Early in the internet, we were using ISO 88591 for all internet documents. It was like the universal standard. Nowadays, I don't think many people say that their website is ISO 88591 anymore. I remember I used to have to memorize writing an HTML document. This is encoded using ISO 88591. So the nice things about these ISO 8859 encodings is that the 0 to 127 is all the same. It's the 128 to 255 that varies, okay? Which is great if you're using a Latin-based alphabet or if your alphabet can fit inside of 127 code points, right? So Cyrillic languages, I think, worked okay. A lot of languages didn't work very well, and so people started using multi-byte encodings. So we had multi-byte. Particularly our Asian friends who wanted to write their Chinese characters. And so these would typically use 2 bytes. And as you know, that gives you 65,536 possibilities. Okay. The problem is, though, is 65,536 is not good enough to represent all possible, language that you wanted to do. Okay. So that's why Unicode came along. All right. So Unicode, let's talk about some of the details of Unicode and how it works. So current standard is 12.1.0. This is published on May 7th, 2019. So May 7th, 2019, which details 137,929 code points. Okay, you can go online. If you're interested in this sort of thing, you can actually read this 1,000-page document that talks about the course specification. You can look up the code charts. You can look up databases. There's all kinds of things they have available for you to help you find your favorite code point. Okay. Of note, Unicode does characters, not glyphs. What does that mean? Well, if you're an English speaker, you're well familiar that there's two ways you can write a lowercase a. This is one way. And then there's this other way, I don't even know how to do it with handwriting. It looks like this, right? Okay, both of these represent the letter A, okay? So in Unicode, this would be one code point. Even though when you draw it on the screen, you can draw it many different ways. So the glyphs are basically parts of fonts, and characters are parts of Unicode, okay? So code points can represent many things. There is not a one-to-one mapping of characters to code points. Typically, you need more than one code point to represent a character, especially when you have code points with, like, accents or, circles on the top or underlines or some things like that that, modify what that character would mean. Okay. So the valid code points can be from 0x000000 to 0x10FFFF, which is about 1.1 million. Okay. So there's about 1.1 million positions that are open. Some of those are reserved that can never be used. Okay. And those code points represent many different things. Okay. Every code point has a unique name. Okay. And this name is entirely unique. It does not vary. Since Unicode 2.0, the names are fixed in stone and will never change. Okay. So if you want to introduce a new character and you want to use a name that's already existing, too bad, you have to use a new name. Okay. When we talk about scripts, we'll talk a little bit about how these names are chosen. Okay. However, many code points have aliases. This might be the traditional names of these characters or something else like that. And not just that, but there's also informal names. For instance, the name A could apply to many, many different code points in the Unicode standard. Some code points are deprecated. What deprecated means is they're just discouraged. They're not going to go away, but you really should stop using them. Okay. Each code point belongs to a general category. This consists of a major and a minor category. And this is represented with two letters. For instance, LU represents uppercase letters. LL represents lowercase letters. And there's some others as well. So the major categories are, you have letters, marks, you have numbers, you have punctuation, there are symbols, there are separators. These start with Z. And then you have other. And the major is always like the first letter of this, except for separator, which is Z. Okay, and you can look up about the different classes and stuff like that. It's pretty interesting to know. The ones that you probably should know are letters and numbers. Everything else is probably not too important. Okay. There are 16 code planes. And what the code plane is when you look at all the possible Unicode code points, this is the code plane. The first two, the first couple bits there. Okay. Each code plane can have 65,536 code points. Okay, that's more of an organization of how the numbers are organized. We also organize them into blocks. A block is a group of code points in a continuous range. Each code point belongs to a single code block. If it's not a named code block, then we would call it the no block block. Okay, And code blocks do not overlap. And code blocks have a name. For instance, one of the code blocks name is basic Latin. And this covers the characters between 0 and 127, which is also known as ASCII. Okay. There are lots and lots of blocks. Too many to list here. Pick your favorite language. You'll probably find that your language has 1 or maybe 2 blocks. Okay. Each code point also belongs to a script. Okay. The script is a four-letter code. And each script represents a writing system. It does not represent a language, though typically there's a one-to-one relationship. Okay. And the script name is in the name. For instance, it's like Latin, capital letter A. That Latin is the script name. Okay. I could be wrong. Okay. So Latin, capital letter A. Each script is, you'll see the name of the script in the name of the code point. Okay. There's lots and lots of scripts. Okay. One of the particular points of contention in the Unicode standard is Korean, Japanese, and Chinese are sharing a couple scripts that represent the traditional Chinese characters and the simplified Chinese characters. And they have disagreements on certain characters about how to draw them. And the Unicode Consortium has said that those disagreements are glyphs because they're not semantically meaningful. You're still talking about the same character. And so you'll run into issues where if you're reading a Korean document and somebody uses a Chinese font for the Chinese characters, the Koreans will say like, oh, that's the wrong character, and things like that, even though it's not. It's just using the wrong font. Okay, let's talk a little bit about bidirectional. So it's possible to use bidirectional scripts, and I believe that Arabic and Hebrew they go from right to left instead of left to right. I could be wrong. Unicode handles this, and it's sometimes confusing because if you have like 1, 2, 3, 4 listed in the code, so that's the encoding. It'll show up on the screen as 1, 2, 3, 4 written out backwards. Okay, so that could be confusing, but that's neither here nor there, right? If you're dealing with one of the languages, you're probably already familiar with the problems with bidirectional text. Let's talk about UTF8. UTF8 is one of these encoding schemas that when you see it, you're like, holy cow, that's like brilliant. This is like something that, it's like the, what's the right way to put this? It's like the most ideal way to encode anything ever. There's so many good things about it, okay? Ken Thompson and Rob Pike take credit for coming up with this. You might have heard of them. They're kind of famous. And we use this for practically everything. Sometimes you may use UTF-16 or UTF-32. We'll talk about that in a minute. So how does it work? Well, if you have 0 followed by 7 bits, 1, 2, 3, 4, 5, 6, 7, then this is just plain old ASCII. Okay? So ASCII in UTF-8 is just ASCII. It just works. Okay? And Unicode has 0 through 127 reserved for the ASCII characters. That'll never change. Okay? However, if you have 1, 1, 0 followed by 5 bits, so 1, 2, 3, 4, 5, 6, 7, 8, and then the next byte is 1, 0 followed by 6 bits, that gives you 11 bits to work with, which can represent 0x80 to 0x7ff. Okay, so this is 2 bytes encoding 1 Unicode glyph. Really quickly, this is 0x00 to 0x7f. Okay, if the first one is 1110 followed by 4 bits, and then you have 10 10xx xx xx, and then a third 10xx xx xx, that will give you 16 bits to work with, so that you can represent numbers from 0x800 to 0xFFFF. Okay? And then if you have 4 ones followed by a 0, it's 1, 2, 3, 4, 5, and then you have 3 bits left over that you can use. And then you have 3 of these 10 bytes. This will give you 21 bits. which gives you 0x10000 to 0x10FFFF, which is the remaining Unicode code points. So each Unicode code points can be encoded with a single byte, with 2 bytes, with 3 bytes, or with 4 bytes. Okay. Now, the neat thing about this is if you think about, you have an arbitrary string of bytes in UTF-8, and you look at a random bit, random byte, okay? If the leading byte is 0, then you've got an ASCII character, okay? If the leading byte is 110, the leading bits are 110, then you have a 2-byte character, okay? If the leading bits are 1110, then you have a 3-bit character, and 11110 is a 4-bit character. If perchance you hit one that's a 10, then you've hit one of these body bytes, and you could either keep going until you find something that's not 10, or you can go backwards until you find the head of it. And then once you find the head of it, then you can read forward to find the entire code point, okay? It's a very efficient way to store. It's a very efficient thing to do. The nice thing is that when you sort like these groups of bytes, you don't have to decode it, sort, and then re-encode it. It sorts by itself, so it's pretty cool. Note that you can have invalid bit patterns. So if you had 11111 followed by anything, this is wrong. You should never see that in UTF-8. Okay. You should never see 0xxxx 1, 2, 3, 4, 5, 5, 6, 7 followed by a 10 with 6. So this is also wrong. Or, 110 followed by 10 followed by 10. Those things are wrong. So having too few or too many of those 10s are also wrong. You can also have, this allows you to encode invalid code points in Unicode. So it's possible for me to choose one of the invalid code points and put it in this format and get back a UTF string that looks perfectly valid but is actually not, because it doesn't describe Unicode. Okay, I'm going to briefly mention UTF-16 and UTF-32. So UTF-32 says, hey, we're just going to use 4 bytes for every, this is going to take a while to write. And then 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we're going to use 4 bytes for every Unicode code points. It's pretty inefficient, but it's very straightforward. The only question you have is, are you doing big endian or little endian? Okay, and what that means is, let's say we had we had A followed by B in terms of bytes. So we had the byte A and B. Is this encoded as BA or as AB? Okay, and that's the endianness of when you're using multi-byte formats. Now, UTF-16 works a similar way as UTF-8. If you have 0, 0 followed by 1, 2, 3, 4, 5, 6, and then 8 more. This will give you 14 bits, I think. Yeah, 14 bits. And then if you have 1, 1, 1, 1, 0, 1, 1, 0, XX, and then XXXX, XXXX. That's 1 16-bit, and then that is followed by 1101 11XX XXXXXXX. This will allow you to get, let's see, 8, 10. This will get you 20 bits of encoding. The only question is a big endian or little endian, and so UTF-16 documents should start with something called the BOM, the byte order modifier thing. It tells you whether you're using big endian or little endian. You can also infer it just by looking at the code, seeing like which ones are encoded how. It should be able to tell you. If you see, for instance, these two reversed, you'll know that it's supposed to be one way or the other. You can also specify, if you know what it's supposed to be and it's guessing wrong, then you can UTF-16BE or UTF-16LE if you know what it's supposed to be. Okay. All right, so I briefly mentioned those. Finally, I wanted to talk about everything that you might ever want to know about encoding and decoding in Python. So, as you know, s.encode does UTF by default, and b.decode. Remember, S and B are strings and bytes. Okay. You could also specify the encoding. Like, for instance, you can say UTF-16, and same when you decode. And this will work. If there is any problem with the encoding, it will raise a Unicode error. And this could occur because it couldn't encode the sequence of Unicode that you have, or it couldn't decode it. Okay. You could override what to do by using the errors parameter. By default, this is strict, which means raise an exception. This works for both encoding and decoding, by the way. You can also say errors is equal to ignore. In that case, if there's any problem with the encoding, it's just going to ignore the error and try to continue. Okay. You can also say replace. Replace will use the Unicode FFFD when decoding invalid encodings, and when encoding, it will give you a question mark. Okay, so you'll see a question mark where it can't figure out what to do. There are two others that I'm going to mention. I'm not going to write them out. XML char ref replace and / replace and name replace. In these cases, what it does is it takes the invalid code points and replaces them with either an XML reference, / reference like you'd see in the Python, escape strings, and also the name. The one that I do want to mention is surrogate escape. So surrogate, and what this does is when decoding, it replaces surrogate codes with something that's between UDC80 to UDCFF. Okay, and these surrogate codes are used so when you go back to encode it again, it will turn it back to the original byte. So if you take a bad UTF-8 encoding, you decode it using surrogate escape for the errors, and then you encode that, you'll get the original byte sequence back. Okay. Now, this is a problem because if you tried to encode this with these surrogate escapes and you didn't specify surrogate escape, it's going to raise a Unicode error because it doesn't know how to encode these. Okay. So what you can do is you can do surrogate pass. And what this will do is it will keep these codes in, what's the right way to put this? It will allow these codes to pass through without changing them. Okay, so that's something to think about, something to look at. If you want to, go look at the codecs module. It's part of the Python standard library. This will tell you a whole lot more about encoding and decoding, more than you ever wanted. If you want to write your own new encoder or decoder, you can go there and do that as well. In conclusion, you are living in fantastic times. You really don't have to think very hard about encoding anymore. UTF-8 is virtually the standard everywhere. And because of that, because Python 3.7 has adopted that standard, everything is easy. You can just say encode and decode and everything should work. If you are interested more in Unicode, I encourage you to go read the standard, go read the Wikipedia articles on it. There's a lot to learn about Unicode, and expertise in Unicode is greatly appreciated, especially when people run into these errors. Typically these errors don't arise until you try writing your program or adapting it to other languages. Anyway guys, I hope this was helpful. Take care and bye-bye. Thank you for watching this video on the theory of Python by Real Physics. Be sure to subscribe and ring the bell, like and share this video. You can find me on Discord or support me on Patreon. Links are in the description below. Thank you so much. Have a great day. Bye-bye.